The graphic contest has few limitations. The first one is we need to identify the number of C, which is the central observations, to be omitted, and also we need to identify the X variable with which we want to order the observations. So here we're going to look into another test which is called Bruce-Pagan LM test. So this is a statistical test whereby the structure or the framework is the same for all hypothesis testing. We need to have H null and H1. Our H null will be there exists no hetero, and our H1 will be there exists hetero. And we need to know the alpha, we need to get the test statistic, and also we need to know the critical value, and then we decide whether to reject or do not reject H null. So in Bush-Pagan LM test, the first thing is we need to estimate the OLS, and from the OLS we need to obtain the residual, and then from the residual we square it, and then we run the auxiliary regression, meaning we regress UT hat squared on Z's. So these Z's will be the X values. So once we regress ui hat squared on the z's, we need to compute the test statistic. So the test statistic will be the sample size multiplying with r squared, whereby this r squared is actually the r squared from the auxiliary regression. Once we have the test statistic, we need to compare with the critical value. So here LM stats here is following the chi-square distribution. So in chi-square distribution, we need to know the degrees of freedom, whereby degrees of freedom here is going to be p minus 1. So p minus 1 is basically just the number of regressors. So here in the model, you have ui hat squared on x's or the z's, and then you have this a1, which is the intercept. So starting with from 1 to p, meaning this is the number of parameters including intercept, and therefore the degrees of freedom here is the number of parameters minus 1 minus the intercept. So we have the degrees of freedom for chi-square. So once we compare with the critical value, then we decide if it is larger than the critical value, so we reject H null and then conclude that there is significant evidence of heteroscedasticity. So if you're using the same data set in the early lectures, okay, suppose you want to do the LM test in E-views. So first we need to estimate least square y, c, and x. Okay, and then we get the estimation result, and then we go for the view. And then when we go to view, we go for the residual diagnostic, and then we go for the heteroscedasticity test. Okay, so in heteroscedasticity test, we can choose the Bush-Pagan. Okay, and then you see here the dependent variable is receipt squared. So actually is the same as in the slide is the ui hat squared. Okay, so this is the result for the BPLM test, whereby we have this is the test statistic, whereby the test statistic is the n observation multiplying with r squared. So r squared and multiply with n, you get 2.3235, and when we compare with the p-value here, so since it's given straight away the p-value, and then we look, it is 0.12, which is larger than 0.10, so meaning we fail to reject H null. So we are able to reject H null, meaning that there exists that it does not exist any hetero. So actually it is suggesting homoscedasticity. So for white test, the structure is the same, whereby we need to estimate the model by OLS and obtain the residuals. But here in white test, we are regressing UI hat squared, okay, but not only on the axis, but also on the squared terms and also the interaction. So suppose you have two independent variables, x2 and x3. So you're going to have another term x2 squared and then x3 squared and also the interaction x2 and x3. So this is the auxiliary regression. YT hat squared on these variables, and then to compute the test statistic is the same as before, whereby it is n multiplying with r squared, whereby this r squared is from this result from the auxiliary regression. And here also is the same, that if the LM stat is larger than the critical value from the chi-square table, then we reject H null. And if we reject H null, we conclude that there is significant evidence of heteroscedasticity. So here in eViews, again, suppose you're using the data on consumption and income, and then you regress Y on X, and then you have this estimation output, and then you can click view again and go for residual diagnostic and go for heteroscedasticity test, and then you can choose the Y here. Okay, so include Y cross term, so you're okay. So if you look at the result here, okay, so since this example we have only one independent variable, so basically it will be only the x squared of it and there's no interaction. But if you have two independent variable, again in the model you are regressing the UI hat squared on the first independent, the second independent, the squared of the first independent, the squared of the second independent, and also the interaction. So here it straight away give us the test statistic, whereby it is the n times the r squared. So the test statistic is 2.57, and look at the p-value for the chi-square distribution. So it's giving us the p-value straight away, which is 0.27. So this is larger than alpha, so we do not reject H null. So meaning that it's consistent with BP test, whereby there is no heteroscedasticity. Another example of White's heteroscedasticity test, whereby we have ln y on ln x2 and also ln x3. So this is the ratio of trade taxes, ratio of sum of exports and imports, and also the GNP. Okay, so we want to test whether there exists hetero or not. So the same as previous example, we need to run this regression and we need to get the residuals, and we square the residuals and regress on the axis, the square of it, and also the cross term. So here is the estimation result, whereby we are regressing UI hat squared on ln trade, ln GDP, the square of ln trade, the square of ln GNP, and also the interaction between ln trade and ln GNP. So this is the result, and if you can see, just to highlight, why do we have a second hat here? Because the first variable, the dependent variable is yi hat squared. So that is before you regress. Okay, and then so once you regress, you get the estimated of y. So it is the estimated of the ui hat squared. Okay, so from this we get r squared equals to 0.1148. So we need to multiply with the n, which is 41, and then you get the test statistic, which is 4.7068. So this 4.7068, we need to compare with the critical value from the chi-square table, and here we are using degrees of freedom whereby if you look at the parameter is 1, 2, 3, 4, 5, 6. So it's going to be 6 minus 1. So it's going to be 5 because it is a 5 number of regressors. So if you are using 5% alpha, then for 5 degrees of freedom, it is 11.0705. So the chi-square table is an upper percentage point. So it's a upper, if you look at the upper percentage point of a chi-square distribution, so meaning that under this curve is 100%, so the chi-square value will be from 0 to infinity. So since below this is 100, so if alpha is equals to 5%, so meaning you're going to have 5% the upper tail, and if it's 10%, then it's going to be 10% of the upper tail. So since alpha, so this is the probability. Okay, so if you look at the table, there's a few pages for chi-square distribution. So the second page will give you the 0.05 or 5% upper tail. So you're gonna have, this is the alpha, and then you have the degrees of freedom, which is 5. So you look at the fifth row. So 1, 2, 3, 4. So it's going to, the critical value is 11.0705. So comparing the test statistic 4.70 and the critical value, so it is lesser. So therefore, based on the white test, there is no heteroscedasticity.